In this video, we're going to try to solve a problem using the Polya method, a math problem. The problem is a baseball batter hits a ball 20 meters per second at an angle of 45 degrees above the ground. How high was the ball at its maximum height? And we're going to be trying to use the Polya method of math problem solving, the Polya method of problem solving to solve this. And we remember the Polya method has 4 steps. Well, what was the first step? The first step was to explore the problem. Explore the problem. So let's begin by exploring our problem. Let's keep a running total of the information that we know. Well, first things first. We know that the batter hit his ball at 20 meters per second. So 20 meters per second, this seems important. And, well, the only other number in the problem is 45 degrees above the ground. So 20 meters per second, 45 degrees. And if we look at the vector that this would create, it would create a vector a little bit like this. This is 45 degrees and 20, right? 45 degrees and 20 meters per second. And let's just keep this vector here in mind as we try to create a graph. It could be a good next step in exploring this problem. So let's create a nice large graph of this problem. We don't really need a negative axis in this case. So here we've got time and height. Well, we know that at the start the batter is hitting it at this nice 45 degree angle, right? 45 degree angle. But it won't stay at 45 degrees, right? Because gravity exists. There is gravity, and gravity will be pulling down on our ball. Gravity is an acceleration, so we're going to see some sort of a parabola before we once again hit the ground, right? And that's when the baseball hits the ground. And the problem is asking us, how high was the ball at its maximum height? Well, the maximum height is a point right around here, right? And how high was the ball at the maximum height? Well, you can see right here, if we project this onto the height axis, the height is going to be some maximum height. And this is the entire goal of the problem, is to find what is this maximum height. So let's try to do that. Let's move on to the second step of the Polya method, step 2, which is to devise a plan. I'm going to devise a plan to solve this problem. And, well, what could we use? If you've taken perhaps a physics course in high school, you will know that there is something, an equation that models a situation like this very well. It's called the kinematic equation. A kinematic equation. Kinematic meaning having to do with motion, right? So having to do with motion. And the kinematic equation has 3 components. The kinematic equation has 3 components. It has your acceleration, it has your initial velocity, and it has your initial height. So, well, we know what the velocity is, right? And we're going to make an assumption here, that because we are only talking about how high the ball was at its maximum height, we won't need to consider how far the ball was going. So let's just consider the height. Here. And the height, well, if we draw a triangle, right, we know we have our length of our speed and our angle. If we draw a triangle here that has hypotenuse of 20, it's a right triangle. Well, the bottom, as we know from trigonometry, is 20 times the cosine of 45 degrees, right? 20 times the cosine of 45 degrees. And this is 20 times the sine of 45 degrees. 20 times the sine of 45 degrees. And we only care about the y in this case. So let's plug this in here. we know that our velocity here is 20 times the sine of 45 degrees. And you might think, okay, well, we're kind of stuck. How are we going to use the kinematic equation now if we don't know what the acceleration and the height are? Well, this is where, as in many math problems, you make a reasonable assumption. Well, what's the first reasonable assumption we can make? First reasonable assumption we could make is that the baseball batter is on Earth. And on Earth there is, like we said, a gravity that has been measured, and it has been known for many centuries, that gravity pulls us down at 9.8 meters per second squared, right? 9.8 meters per second squared. So we can say, and I mean, depending on if you're saying that gravity pulls you down, or if you just want the absolute value, this could also be a negative 9.8 meters per second squared. And we're going to use the negative version in this problem. The gravity is going to equal negative 9.8 meters per second squared. And this velocity, by the way, is meters per second. And the height, well, we can assume that the baseball batter hitting this will hit it, just for the sake of the problem, at an initial height of, let's say, 1 meter. 1 meter, no, maybe he's like 1.5 meters tall, and he's hitting the ball like kind of at his chest level, right, and it flies off. So with this knowledge, we have devised our plan. We have created the kinematic equation, and we have all the information we need to set up the kinematic equation. So let's do that. Let's set up our equation, our kinematic equation, and move on to step 3. So, well, the kinematic equation is 1/2 acceleration times time squared plus your velocity times time plus your initial height, equaling your height at any time. This is, I'm going to add a height not. This is meant to be your initial height, equaling height as a function of time. So this is a function, and this is a constant. Slightly different, slightly confusing, but I think we can do it. And t is our variable. So with this, let's write down step 3, because we're on step 3 now. Step 3 is to execute the plan. And I think we're going to break the video in 2 at this point. And in the next video, we will work with the kinematic equation that we have discovered, the information that we've assigned to it while devising our plan. We're going to work with this to solve our question. So I will see you in the next video.